Okay, in this screencast, last one, I'm going to talk about electricity and power. And yeah, okay. So you'll remember that electricity is energy per unit of time. So it's work done or energy transferred per second. So power is a joule per second. So power is a joule per second or a watt. Think of a 60-watt light bulb, okay? Well, we haven't talked about this in the other screencast, but current is charge per unit of time. That is going to be on your equation sheet for under electricity. I'm not sure you're going to need to use that, but Q, remember, is a unit of charge. It comes in multiples of 1.6 times 10 to the negative 19th coulomb. That's a charge on an electron. So obviously billions and billions of electrons would flow through a typical wire when it's running with maybe half an amp of current or something like that. So Q is going to be a lot of electrons in that sense. Voltage, you probably don't need to know this, but I'm just showing you this just for reference, is that V, or voltage, electric potential, is it sometimes called, is electrical energy per unit of charge. Don't write that down. It's just part of the derivation for power, so you can see where power comes from. If I multiply I times V, so that's down here, I times V, notice that the Q's cancel out and I get energy per unit of time, which is exactly what power is, energy per unit of time. So it turns out that power is just, in the electrical world, is current times electric potential or voltage. So I times V. But remember, Ohm's law is I times R. Before you get into that, before you get into these other variations of that equation, let me stop here for a minute. I've got current in amps. I've got voltage or electric potential in units of volt. When you multiply those together, you do get a watt. Okay, so that's a joule per second. Okay, and I won't spend time deriving that because it's going to just get into some things that we haven't defined in this class and we don't need to know for this class. So just trust me that when you multiply an amp times a volt, you're going to get a watt. Let's think about a 60-watt light bulb. You know, a 60-watt light bulb, we could figure out how many amps of current are in that 60-watt light bulb in your house, because the power of a 60-watt light bulb obviously is 60 watts, and the voltage in American homes is about 110, 115 volts. Let's just go with 110 volts. So we could easily find the current, because based on that equation that you see down there, current is power over voltage, which is 60 over 110. I'll take this offline while I calculate that. That is 0.545 amps. Okay, so about a half an amp, a little over a half an amp in a 60-watt light bulb. That's an old-fashioned incandescent light bulb. You guys should have in your homes now those curly CFLs that are they're much more efficient. But it'd be about half of an amp of power, which would be, or a half an amp of current, which would be I. That'd be a whole lot of electrons going through that wire for a half an amp. Okay, back to this. So I was starting to say that voltage in Ohm's law is equal to I times R. So if you combine these equations, if I solve for I get V over R. That's all I did, was I divided both sides by R. And, sorry, I'm already deriving the second one. So let's stick with the V equals IR. When I substitute in the I times R for V right here, I get the equation I squared R for P. If I substitute V over R for I get V squared R. So there are two variations of the power equation that use the different variables. Okay, which one should you use? Should you use P equals I times V? Should you use P equals I squared R, or should you use P equals V squared over R? It depends on what you're given in the problem, and I'm going to do an example for you at the end, so you can see different ways to approach it. So again, these are our two equations for power. The IV is one of them, so there's three of them, but here's the two that we just derived with Ohm's law. The one is I squared R, the other is V squared R. This one tends to actually work better with parallel circuits. This one tends to work a little better with series circuits. The reason being, in a parallel circuit, you remember from previous screencasts, the voltage across the resistors is the same. So if this was a 12-volt battery, the high potential would be up here. This would be 12 volts up here. This would be the low potential down here at 0. It's kind of like gravitational potential energy. You get to pick your 0 point. So we'll pretend this bottom leg is 0, or we'll select it as 0. That means the voltage difference would be whatever V is for this battery. If it's a 12-volt battery, that would be 12. Okay? So, so when you know the voltage across the resistor, it's really easy to find the power dissipated by the resistor using that equation on the right over here. If you have a series resistor, the current is the same through all the resistors in series because of conservation of charge. You've got to have the same amount of charge, and Kirchhoff's rules tell us that too. Kirchhoff's law says that the junction rule says that any current that goes into a junction has to have the same current coming out of the junction. Well, this is just one constant loop. So you've got one, it's like flow through a pipe. You've got one constant flow all the way through those resistors. So the current's got nowhere else to go. So what happens is you can use this equation on the left more easily instead of trying to figure out what the voltage drop is across those two resistors. What I did down here on the bottom is I found the equivalent resistance. So I solved for the current, I, in terms of the equivalent resistance for the circuit. Since these are two resistors in series here and here, all I did was I divided V by the equivalent resistance to get an expression for the current in terms of voltage and the resistance. Over here, since I have a parallel circuit, remember how you solve for, from a previous screencast, how you solve for the equivalent resistance in a parallel circuit is you have the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistors. So I just put that all into one equation over here on this side. When I put that all together, you get the equivalent resistance of two resistors of the same resistance R. By the way, that resistor R for both circuits is the same resistor. So I'm just calling it resistance R. So the R's in all four of those resistors in the two circuits are the same. So it turns out that the equivalent resistance of these two in parallel on the right side is just R over 2. It's half of the resistance of a single resistor. So when I put that into Ohm's law for the right circuit for I1, if I have an equivalent resistance of R over 2, then I divide V by R over 2. That's, by the way, that's like having a circuit like this. It's like having a circuit with just one resistor. That's what equivalent resistance is, of R over 2. So I1, to calculate what I1 is, you just use Ohm's law, V equals IR. I solved for I, so I divide V by R over 2. That's what I did right here. And then my 2 comes up into the numerator, and my current is actually 4 times bigger, I1, than it is in I. I'm sorry, I1 is 4 times bigger than I is in the series circuit on the left. How can this current be 4 times bigger than this one over here that's got these two resistors in parallel? Remember from a previous screencast, when you add another branch here, you add another resistor, it's like adding another pipe. So I've got a pump here. This is like almost like a water pump, only it's electricity. So it's pumping, it'll pump as much water as the pipe will take, and if I add another branch, I can pump more water through it. So I can, the rate of electron flow, which is analogous to the rate of water flow, gets greater. So it's kind of surprising, but as I add more resistors in parallel, you're going to actually get more current flowing through the additional branches. So why am I doing all this? Because the goal is for us to get to this next screen here and explain how to calculate power. So power dissipated, I should have commented on that before, those two equations with resistance in them are sometimes called power dissipated, because resistors dissipate power. So when you have an expression for power with R in it, you refer to that as the power dissipated in the circuit. Okay, here's my current I again in this, and we've already solved for V over 2R is my current. So I'm going to use the form of the equation P equals I squared R, and I'm going to substitute that value of I in. So V over 2R squared down here in black times R, I get V squared over 4R. And notice how one of the R's in the denominator cancels out with the R right here. Okay, so this is my power dissipated in the circuit, in the two resistors on the right hand side. Over here in the parallel circuit, I've got a little different situation. Actually, I'm sorry, this is the power dissipated in each one of those resistors. So this is the current passing through each resistor is V over 2R. So when I multiply, when I use this form of the equation and I multiply the current times the resistance R, then I get V squared over 4R. That's this right here. That's the amount dissipated, that's the power, in each resistor. Think of it as a light bulb maybe, okay? So that's a power dissipated in each resistor. Now over here on the parallel side, I could actually more quickly, rather than using current, even though I do know my current right here, rather than using current, what I think I'll do is I can just jump right to the bottom here to this equation, V squared over R, and I know that my voltage drop across each resistor is whatever the voltage of my battery is. So I just called it V. So the voltage drop is V, so my power dissipated across each one of those two resistors in parallel is V squared over R. And that is 4 times P2, the amount of power dissipated in the resistors in parallel is 4 times greater than P1. So by a factor of 4, that's what I have here. So P2 is greater than P1 by a factor of 4. That means if these were light bulbs, that those two resistors in parallel would burn more brightly than the ones in series. They have more current going through them. They have the same resistance. So I squared over R is going to be a larger amount. Now notice that up here what I have done, back up to this point where I'm darkening it with this blue arrow, the I1 we found from the previous slide is 2V over R, and it splits into two branches, I2 and I3. Well, because these are exactly the same resistors, the resistance is going to split evenly. So I have half of I1 in each one of those resistors, current passing through each one of those resistors. So it comes out that the current through each one of those resistors is just V over R. So I take the 2V over R and I divide by 2 and I just get V over R. Okay, so that is another way. If I wanted to now go back and use this version of the equation, I could, and I'd get the exact same answer that I've already gotten, which is this guy right here, just using the current instead of the voltage. So power dissipated in a resistor determines how much wattage is being used up. So you're given wattage in basically the battery provides the wattage for the circuit, and then the power is dissipated by the devices that you have in the circuit, which in this case I just showed resistors, but they could be your toaster at home, they could be televisions, they could be electronic devices you have plugged in, or they could be light bulbs. Now I just want to make one more comment and I'm done here. I'm going to the next slide, and I'm going to talk real quickly about this kind of strange situation where you might say, okay, if resistance increases, does the power dissipated go up or down? these two equations might seem to be conflicting, because if resistance goes up over here, power dissipated goes down, right? So if in this one, if resistance increases, power decreases, okay? But over on this one, if resistance increases, you might say, well, then power must increase as well, because resistance is on the right-hand side of the equation. They look like they're directly proportional. But remember Ohm's law. Ohm's law says V equals I times R. So for every factor by which R increases here, let me show it over here. If R goes up, I goes down by the same factor. Okay, that's Ohm's law. So if I double R, I is going to go down by a factor of 2. So as it turns out, if R goes up down here in this formula, if R goes up, I has to go down because of Ohm's law by the same factor, and I is squared. So it turns out if R increases, P goes down because I goes down by the square of the change of R. So these are consistent, even though it doesn't look exactly like that. They are consistent with each other. Okay? That's all. Good luck.